Here's an example that employs a concept that's coming up. After electronics, photons are incident on a semiconductor, and if they have enough energy, they will ionize silicon atoms and create electron hole pairs. Quick little animation of how that happens. And you have this pair of electrons and holes that goes out into the semiconductor. They don't last forever. Remember, we talked at one point about the recombination lifetime, and so they live for about a microsecond in the semiconductor before the electrons and holes find each other and recombine and make a nothing after that. We're given that photons are hitting with suitable intensity, that electron hole pairs are generated at a rate of 5 times 10 to the 14th per second. So that's a given. Don't ask me how I know, it's just given. This particular silicon semiconductor was doped with a concentration of 10 to the 7th donors per cubic centimeters. So it's an N-type semiconductor. Majority carriers are electrons. And we want to find the hole concentration far into the illuminated region and then dark region. What I mean is way over here for the dark region and way over here for the illuminated region. We're not going to figure out the hole concentration right yet, right in the vicinity of the little area here, because there's diffusion. These holes are generated all throughout this uncovered region, and they diffuse into the covered region a certain distance. And so we will work on that next. We'll work on that next time, 2 times from now actually. Holes are composed of 2 populations. They're the equilibrium concentration of holes, and there's the excess carrier concentration of holes. We have to account for both of them, P sub 0 being what you have in equilibrium, and P prime being the excess hole concentration. Now we calculate them based on the doping actually. That excess hole concentration is affected by diffusion into the uncovered region. It is X dependent. Well, it's X dependent simply if you're in the illuminated region, it's something, and if you're not in the illuminated region, it's 0. And around the illuminated region, it's gradually dropping off due to diffusion. So we'll work on that X dependence another time. We can figure out the equilibrium hole concentration from the electron carrier concentration, which is known because the doping level is given, right? If we assume 100% ionization, the electron concentration is the donor dopant concentration, so that's known, in which case we can calculate the equilibrium hole concentration from the equilibrium carrier statement, the law of mass action. P sub 0 is N sub I for silicon squared over the electron concentration, which is known to be 10 to the 17th. So the equilibrium hole concentration is known, and it's only 1,000 per cubic centimeter. So there's not a lot of holes in this semiconductor until we turn on the light. And the hole concentration will change dramatically now because we have a generation rate. And you notice that big G was kind of large. It was, that was a 10 to the 14th per cubic centimeter. We have this excess hole concentration we can talk about. We have a generation rate. 5 times 10 to the 14th holes are generated per cubic centimeter, I should say, per second. Fix that right now. We know also that those holes don't stick around for a long time. They're excess holes, and there are excess electrons, and they find each other roughly every microsecond. So there's a turnover. Yeah, you generate 5 times 10 to the 14th holes per second, but there's a turnover of 1 microsecond where they all get gobbled back up again. And so really what I should say is every microsecond we make holes at the rate of 5 times 10 to the 14th per second, meaning every microsecond we make 5 times 10 to the 8th holes and destroy them. And then we make, next microsecond, we make them again and destroy them. And the next microsecond, so we make this 500 million holes every microsecond per cubic centimeter and destroy them and do it all over again. So we now know that at P prime, the excess hole concentration is 500 million holes per cubic centimeter. We go with the statement that N prime equals P prime. The excess hole concentration is the excess electron concentration. I should preface this, in equilibrium. We're in equilibrium with the generating source, with the photons. Okay, the light source is a constant. I should be a little careful using the word equilibrium here. We're making holes and electrons at the same rate, and the holes only go away because they find an excess electron to go away with, so they go away at the same rate. So the excess electron concentration is also 5 times 10 to the 8th electrons per cubic centimeter. Now compare that to electron concentration that we have, which is, what was that, 10 to the 17th? And it's a lot less. So really the excess electron concentration is irrelevant. And when that's the case, you call that low-level injection. So low-level injection is when the number of excess majority carriers is negligible compared to the equilibrium value of majority carriers. That means then that the current through a semiconductor really just depends on the excess minority carrier concentration. And that's going to be our topic next time. We're going to find the current due to excess minority carriers, which is the only current that matters. And that's our next topic. We'll get to that next.